Hi, welcome back. We're going to continue our discussion on chain rules, and we're going to be looking at more than one independent variable. So let's take a look at part C. In part C, we're looking to take the derivative of z with respect to t, because remember that's what our directions have asked us to do. But you might notice something different here. Here they say x is natural log of xy plus y cubed, and y is a function of x squared plus 1. And you might be saying to yourself, there's no t! Well, that's okay. We are going to establish that independent variable. So to do that, we're going to keep it very simple. Let x be t. Think back to pre-cal. Remember in pre-cal when your teacher would say, let's write parametric equations, y equals x squared. And you were like, I got it easy. Let x be t, y be t squared. Bam, parametric. Keep it simple. You can let t be anything. You let b sine t if you want to. I mean, that's crazy. But if we let x be t, we can say then y would be the cosine of t squared plus 1. So we're going to establish our variable here. So I'm going to use our partials rule. So we're going to take the partial of z with respect to t, and that's going to equal, well, dealing with the x's, we have to take our partial of z with respect to x. That's the outside, but remember we're going to plug in t for x, so we've got to take the derivative of that x with respect to t. And I do the same thing with the y's. The partial of z with respect to y times the partial of y with respect to t, or the derivative of y with respect to t. And again, you should be able to do these kind of like in your head. Let's deal with the first one. The partial of z with respect to x. Oops, that's a product rule here. So we would take the first, which is x, times the derivative of natural log of xy, which is 1 over xy, times the derivative of the inside, which would just be y, plus the second, natural log of xy, times the derivative of the first, which is 1. And there's no y here, so that just becomes 0. And I'm going to multiply this by the derivative of x with respect to t, which is just 1. Then I do the same thing for the y's. Okay, I don't have to do a product rule here, but I will get x times 1 over xy times the derivative of x, the derivative of the inside with respect to y, which is just x. And that becomes plus 3y squared. And we're going to multiply that then by the derivative of its inside, which is this with its cosine t squared plus 1. And that's just going to become times a negative sine of t squared plus 1 times 2t. And I ran out of room. And there is your derivative right there. Now, of course, again, what you may do if you get bored, replace the x's with t's and the y with the cosine t squared plus 1. Right, so let's take a look at part D right now. Now, part D is a little bit different. Now, here, notice when we have this function, z is a function of x and y. But we are replacing the x with g, which is a function of s and t, and h, which is a function of s and t. So in other words, our insides have two independent variables. So we have to be more picky about what are we taking the derivative with respect to. Well, the first one says we're going to take the partial of z with respect to t. So we can do that, the partial of z with respect to t. Well, what does that mean for us? Well, if I'm taking the derivative with respect to t, that means we treat all the s's like a constant. So we can treat s as a constant in this case. So when we take the derivative, we're going to take the partial of z with respect to x. And then that's the outside. There's our outside derivative. And we're going to multiply that by the partial of x with respect to t. And there's our inside derivative. And then we do the same thing with the y's. The partial of z with respect to y. There's our outside derivative. And I'm going to multiply that by the partial of z of y, with respect to t. And there's our inside. So basically we just ignore the s. They're a constant. And let's take a look here. Let's take a look at the partial of z with respect to s. We would, same thing, we would get the partial of z with respect to x times the partial of x with respect to s, plus we get the partial of z with respect to y, and the partial of y with respect to t. That's what we're looking at. S. There we go. And those will be our two partials. Now, another thing to remember, since we're dealing with s and t, we are now looking at a surface, not a trace, not a line, or not a line in space somewhere, or a curve in space. All right, so let's take a look at the next ones here real quickly. Now, for our next example, we're going to back away from the chain rule a little bit. We are actually going to talk about implicit differentiation, and maybe a shortcut to help us out with that. All right. So, last year we learned implicit differentiation, and we had this on our last test and quiz, and these are kind of lengthy to do. But today we're going to take a look at a shortcut. We're going to extend what we did last year to find the derivative of w using implicit differentiation. Now, when we think about the derivative of w with respect to x and y, right here, the first thing we're going to do, now remember, we're going to take the derivative of w with respect to x. And if we think of our total derivative, which we're looking at right here, if we're thinking of the total derivative, our rule says we would take the partial of our function with respect to x times the derivative of the inside, dx dx, plus the partial of with respect to y times the derivative of y with respect to x. So we're taking the derivative, each one with respect to x. This is my chain rule right here. There's my outside derivative, and there's our inside derivative, except for we're taking the derivative with respect to x. Now, last year we remember that we never write dx dx, and we saw this last year like if we were taking the derivative of something like, let's say, x squared plus y squared equals 3. We say this would be 2x dx dx. My derivative, there's my outside function, and the derivative of x is just 1. Plus, my outside function becomes 2y. The derivative of y, my inside, becomes dy dx, and that becomes 0, of course. But we never write the dx dx because we know that that's just going to become 1 all the time. Now, if the function is equal to 0, there's a rule here. If the function is equal to 0, then the derivative must also be equal to 0. Therefore, I can rewrite this as dy dx is equal to there's my chain rule, there's my total derivative right here. And again, remember, we don't worry about that. I set that equal to 0. Well, if we solve for dy dx, notice what we get. We would get negative the partial with respect to x divided by the partial with respect to y. And we can extend this to even more variables. For example, let's let w be a function of x, y, and z. I can therefore say if I want to find the derivative of w with respect to z, I could write that as the sorry, let's make this a x. There we go. If I want to find the partial or my implicit, my derivative of x with respect to z, I could write this as negative the partial with respect to z divided by the partial with respect to x. And we can go forward with more and more of those. If I want to find the derivative of y with respect to x, this will become negative the partial of the derivative, the partial with respect to x, over the partial with respect to y. So let's take a look at an example. Here we have a function, f of x, y. We have this surface right here, x, y cubed plus y squared minus 5y minus x squared plus 4. Now notice it must equal 0 for this to work. So let's say we want to find the derivative of y with respect to x. Well, if the function is equal to 0, my rule here says this is just going to be the negative, the partial with respect to x, divided by the partial of the function with respect to y. And I can do that real quick. Ready? Let's see here. What would the partial with respect to x be? Well, this is just 0, 0, 0, because they have no x's. So I would get on top just negative 2x. Don't forget there's a negative on the outside there. And the partial with respect to y, well, that's going to become 3y squared plus 2y minus 5. So this just becomes 2x over 3y squared plus 2y minus 5. And we can verify this from using our skills from last year in calculus. If I want to find dy dx, right, this will become 3 dy dx, y squared plus 2y dy dx minus 5 dy dx minus 2x equal to 0. And you can see if you bring the 2x over and divide all by that, you would get your same answer right there. All right, so what if we were asked to find the partial of x with respect to y then? Well, then my rule just says becomes negative the partial of y over the partial of x. And you just basically flip it. So you get 3y squared plus 2y minus 5 over 2x. So this is going to be our rule for implicits right there. Right. So let's see here. So here we have a function with respect to x, y, and z. And that's going to equal 3x squared z. Now notice we have three variables here. It must equal 0, which it does. I mean, if it's equal to f of x, it's going to equal to 0 there, so that's okay too. So let's find the following derivatives. Let's find the derivative of z with respect to x. And let's find the derivative of z with respect to y. Now, what I tend to do is I go ahead and list out the partials. fx, fy, fz. To find the partial with respect to x, we get 6xz minus 2xy squared. The derivative with respect to y becomes negative 2x squared y plus 3z. And the derivative with respect to z, 3x squared plus 4z plus 3y. And that 5 is like, what about me? I'm sorry, you ain't got nothing for us, you're dead. All right, so now if I can find those derivatives, the derivative of z with respect to x. So remember, this is my implicit derivative. Now, we had this question similar to this on our last test, and it was very hard to solve. But my new rule just makes it shorter. So this is just going to be negative the partial of x divided by the partial with respect to z. So the partial with respect to x, so we get negative, and I'm going to go with 6xz minus 2xy squared divided by the partial with respect to z, 3x squared plus 4z plus 3y. And this will even work with the derivative that we did last year in calculus. So try the derivative of z with respect to y. My rule says the negative the partial of y divided by the partial with respect to z. Of course, the bottom is just 3x squared plus 4z plus 3y. Don't forget your negative. The y is 2x squared, negative 2x squared plus 3z. And of course, you can distribute that if you feel like it. I'll leave it like that, and that's fine. All right. So I hope you guys enjoyed this video. Go to part 3. Got one more example to go over with you guys.